All right, so we're going to do, we can talk about the geometric meaning of all this, and then we're going to do solutions appertaining to it. No, there we go. All right, so analytical solutions are not always possible or practical. In differential equations, that becomes more true than ever. In fact, the amount of differential equations, if I just randomly gave you an equation that was a differential equation, the chances of you being able to solve it are zero, right? It's just mathematically zero, right? I mean, yeah, we solve tons of them, but those are all very special classes. But so it's not always practical. So another way of getting a difference is use a qualitative method and numerical methods. And so we're going to start with the qualitative methods, which is just kind of looking at graphs. So from calculus, we know that this, the derivative of a function, is the slope of the function, right? Hence, the solution, hence the solution curve, whatever that solution curve is, that passes through a given point must have a slope equal to whatever that value is. And so we're just going to end up graphing all these slopes, right? So direction field is nothing more than all these you draw these little mini tangents to represent all these graphs, all these slopes, not graphs, slopes. Yeah. At each point. And then if you are given an initial point, you can watch it kind of draw itself. And it's really quite interesting. So here, let's just kind of do a kind of a visual representation. So here, if I have some function, right? Here I'm given some function y of t. And here, if I drew just a little mini slope, right? This will be, if I knew my derivative is equal to this, the slope here is f of x naught y naught. So the slope of this little mini tangent, right, is equal to f naught y naught. And the same here, be here, and it'll be the same here, and the same here. And so you can keep drawing these tiny little mini tangents all across the thing. So, here, let's actually draw a directional field. So let's do one for something really quite simple. So here we're going to have our derivative. Our differential equation is y prime is equal to y minus x. So this right here is going to be my f of x, y. So let's actually kind of draw this real quick. So what do we have here? So let's just start filling it out. So at the point 0, 0. So at the origin, if I have the function of 0 minus 0 is equal to 0 minus, or function of 0, 0, 0 minus 0, which equals 0. Here at 0, comma 1, what do we have? We have f of 1. And so remember, this is x and then y, so this will equal to 1 minus 0, which is 1. And here we can do it 0 minus 1. And so we have f of 0 minus 1. And I have minus 1 minus 0, which equals negative 1. And we can keep doing this. And so here I have a slope of 0. So here I'm going to actually draw these in red so it's easier to see. So here I have a slope of, let me make my 1, 2, 3. Let's make it so I have a little bit more room on this draw. So I'm going to give myself 2 tick marks per thing, right? And the same here. All right, so here at 0, it's 0. And so I have this kind of flat line right here. Here at 0, 1, so up 1, I'm at 1 up. So it's kind of a line that looks like this. And here at this, it's negative 1, kind of looks like this. Here at 1, 1, it'll be a flat line again, right? And here at 2, 2, it'd also be a flat line. Here at 1, 2, it'd look like this. Here at 2, 1, it looks like this. And here at 0, 2, it'd be 0 minus 2, and so it'll be even steeper. And so this looks like this. And so here you can roughly draw in the entire this. And so here I can draw a whole bunch of slopes, right? And so I can roughly draw this in. This will be a little bit steeper. This will be a little bit steeper, and this is even steeper, right? And so you can draw in all this. Now we're going to do this by hand? No. And all of a sudden, I always use a cute little program to do this, but I fear it may not work right now. Yeah, because I always used, nope, not that, go away. Shoo. I always use this Java tool, but I don't have my Java launcher working. Let's use Wolfram Alpha. I'm pretty sure I can do directional fields in Wolfram Alpha. Ah, here we are. No, we're going to do them by hand. I'll show you how to do this. I have to install my Java. My Java's dead. They used to be a cute applet. Let me find something later. So let's do the next two, and then I'll show you how to do numerical methods, but we do that in a spreadsheet. All right. All right, so let's do this one. All right, so we're going to draw a directional field for this. Yeah, so let's draw a directional field. So here I have, oops, I have one too many Y's. I have one too many Y's in this notes. Please get rid of this Y. There we go. So let's do this one, because this one I can actually fill out the whole thing real fast for you, and I can show you things. So here, I have y prime is equal to 2t. Does it care what value of y we're at? No, right? It doesn't. And so here, when t, let's make this t, let's make this y. When t is 0, I always have flat lines. When t is 1, let's go ahead and use our same, I'll have, it's at 2, so it'll be like this. And then when it's at minus, if it's at minus 1, it'd be minus 2. So it looks like this. Oops. I have some drift. And then here it'd be even steeper. Here it'd be even steeper. And then here it almost looks flat, right? And so this is directly what this is. But what derivative is this? Well, we know that this is just t squared plus some c, right? You know, this is what y is. Y derivative is t squared plus some c. But here, given any c, what we can do is here, let's just say c equal to, say, 3. Here at 3, we come here, we can follow the lines and go up and go up and go up, and here and go up, go up, go up. Okay. And so here, given a c, we can produce these values. Let me show you in the book after we draw 2 more, and I'll show you some nice ones. That way I'll make sure the cut, show something in the book and then cut back, because I'm not allowed to show the book on YouTube for copyright issues. Here, once again, we can have something, and this time it doesn't depend on y. We call this autonomous. And so let's go ahead and let's do a couple points here. And so here, when y is 1, so let me actually be really strong about my notation. Let's make this 1, let's make this 1, let's make this 1, and let's make this 1. All right, so I have 4 units. And so let's draw our slope in red. So here, when I'm at 0, when my y value is 0, it's 0. So I have this flat line like this. When I'm at 1, it's also 0. when I'm at a half, when y is equal to a half, what do I have? I have d, my y prime is equal to 4 times a half times 1 minus a half. What does that give me? It gives me 1, right? And so here at a half, I'm just going to have the value of 1. And then here at y equals to 3/2, right? 3/4. Let's just do y equals to 3/4. Then y prime is equal to 4 times 3/4 divided by 1 minus 3/4. So this is a fourth. So here I get 3. So I get, here I get these fours cancel. Here I get a fourth, and so I just get 3/4, right? And so it's still positive, but slightly less positive, right? And let's say y equals to 9/10, just for kicks, right? 9/10. Here I get y prime. So here I'll have 4 9/10, and then I'll have minus 9/10. And so when I calculate this all out, here I'll get a tenth, right? So I'll get 36. And then I'll have a 10 and 10 on the bottom, so 100th, right? And so that's pretty flat. So it looks like this. Okay. All right, so I'm going to make a big red star right here so I can cut to the actual answers on these things. Hi. Big red star. We'll show this, and then we'll show you how to do it numerically. Let me find a program that's free for you guys to use that works well for drawing these fields, because I do not want you to draw these by hand. I want you to do, like, if I ask you to do something by hand, just show like 9 of them. All right, let me grab 2 things real quick. Let me grab this, and let me grab this. All right, let me open these 2 in Photoshop. That way I can pretend they came from somewhere weird. All right, open this up in Photoshop. All right, so here's a directional field, right? There's our directional field. So this is our directional field for 2t. And so notice here, so given anything, so if I started here, I could pretend what the solution is. I just kind of follow until I hit my next line, then follow that until I hit my next line, then follow that until I hit my next line, follow that until I hit my next line. And I can slowly and surely draw in a solution curve, right? I mean, it's not super precise, but it's something you can kind of guess, right? You can see that the solution vaguely looks like this. And if I started at a different point, I can see here I go down, down, vaguely kind of turn, come back up. And so I can vaguely picture the solutions. Okay. So you see how you can vaguely picture solutions once you have a lot of dots in there. So let's look at the other one we just did. All right, so here's what the solution curve looks like for the one we just did, for the 4y minus 41. So here, notice if I start here, I'm at 0, I can just draw a nice happy line, and this stays 0. Here, if I have another one here, this one just kind of stays there. And that's true, right? If my derivative is 0, my change to my y will be nothing, and so I'm going to still stay at the same y. Does that make sense, right? At these points. So for here, when y is 0, if my initial condition is y is 0 is 0, well, my derivative is 0, right? So I'm not changing. So it's just going to stay 0 forever. If it's 1, well, my derivative is 0. So this is not going to change. But here, if it's anything else, just go to my little screenshot. If it's anything else, let's go ahead and do this in green. If I start here, notice it kind of comes up, comes up, comes up, and then it slows down and goes like this. And so here I can kind of picture my solution curves depending on where I start. And here I'll draw this one in green too. And what it means by autonomous, it means that this solution looks the same as this solution, right? or here in the, I guess teal is a terrible color. Let's use brown. This solution looks the same as this solution, just shifted over. Okay. And then here we have our other solutions where this goes down and this goes down. And so here we can kind of picture the solutions just by drawing all the little things. And no matter how terrible that function is, we can plug in values and pull out numbers, right? No matter how awful it is. And so this is just a really efficient way of doing it. So let me show you the numerical way, and we'll call it for class today. And then I'm going to do a little bit of research tonight, find out what's a good free way of drawing directional fields and ship it to you. Because I was just going to show you the other one, but I opened it up during office hours and realized it wasn't working and didn't have an opportunity to restart my computer since then because I'll have to install something. All right, so here's the numerical method by Euler. Why am I in a fun color? Let's do this color here. So here, given this, so what can I do? Well, here, let me show you. It's easier to explain what we're going to do graphically. So let's say I start at some point, right? Let's say I'm given some x naught equals some y naught, right? Say I'm given this point right here, right? I start here. Well, what can I do? Well, I can just say, well, at that point, I can find out what my slope is, right? I can draw some little mini tangent line, right? And I can do the slope. And then I can walk that slope some x distance, right? And get to a new point right here. And then at this point, I'll have a different tangent line. And then I can walk that some distance and walk it here. And we're going to call this distance delta x. Often I'm just going to use h for my step size. This is the more popular step size. And delta x. Then what's this? Well, this is just how far have I gone up or down? Well, that's just what is my slope times my distance, right? Rise over run. And so that just tells me exactly how far I've gone and how much I've done it. And so here's just geometrically what we're doing. We're just going to walk a little bit in this. And it's given by this equation here. So we're going to do 2 of these by hand. And then I'm going to open up a spreadsheet and we're going to do the rest via spreadsheet. Okay. Actually, I'm going to do 2 by hand, have you do the third one without me and do this. So let me do this as slow as possible. So let's go back to my blue. All right, so we're going to make a table. We're going to make a table of k. I don't know if k is necessary, right? xk, yk, and then we're going to have our function value of xk, yk. These are k's. You may not know that, but I'll tell you what they are. All right, so let's look at this. So we're going to use this equation right here. And we're going to start with y of 0. So x, the initial x, and 1. And we're going to say this is my 0th step, right? We're going to let our step size be 0.1 for now, okay? So let's show you how this is computed, actually using the formulas. So if I have 0 and 1, I'm going to plug that. This is my f of xy, right? So here, I'm going to plug this into my f. So my x naught plus my y naught, because here I'm at k being 0, so this is x naught, y naught, and this will be f of x naught, y naught. Well, that's equal to 2 times 1 minus 1. 2 times 1 minus 1 is, someone has a Desmos calculator. I'll have to try that real quick. So what do we get here? We'll get this is equal to 1. All right. And so what we do now is we just do the next step. So we do 0. So our next step is 1. My next value. So I'm moving. So x, let's go up to here. So x of 1 is equal to x naught plus my step size. Well, my step size in this case is, so x of 1 is equal to x naught plus my step size, which is 0.1. Let me just write it as this, and then we'll do x1 is equal to 0 plus 0.1, which is equal to 0.1. now my y of k is equal to, so my y of, let's go now to figure out y of 1 is equal to y naught plus f of x naught y naught times my step size. And so in this case, it'll be y naught plus f of x naught y naught times my step size. And then here it'd be 1 is equal to 1 plus 1 times my step size, which is 0.1. So I get this to be 1.1. And so I plug that in. Then I figure out what is f of x1, y1. Well, that's just equal to 2 times 1.1 minus 1, which is equal to 1.2. You plug that in here. We'll go to our next step size. Here, it'd be x naught plus this, and so it'll be x1. I'll go ahead and write out the next one is equal to x1. x1, so x1 is 0.1 plus the 0.1 of my step size is equal to 0.2. Here, my y my y of 2 equals my y of 1. Well, y of 1 is this, so 1.1 plus my function value, which is 2.1, so 2.1 times my step size, which is 0.1, and that's going to equal, hold on, let me do this correctly. (1.22). Yes. And then we plug that all into the formula one more time. We're going to get 1.44. All right, so now go ahead on your own. Try to find 3 real quick. Find step 3. If you can do this, you can do it for any size. I'm going to try this calculator super fast. Oh, that's really nice. Vector field calculator. Yeah, that's good to know. All right, do you guys get solutions? Let me know if you get a solution or not.
Does it start going down or decreasing in value for y in the function of
So
x?
I have y3 equals 3.64. Yeah. So the correct answers here are 0.3, 1.364, and then 1.73 roughly. Okay, so let's do this not by hand. No one does numerical method by hand. So let's just let's just grab ourselves a boring spreadsheet. Hi, boring spreadsheet. You can do this you do not have to use a spreadsheet. All right, so let's just do stuff. Let's just make this my k column. Let's make this my x sub k column. Let's make this my y sub k column. Let's make this my f of x comma y column. And then over here, I like to just have my initial conditions separate, just because I don't like hard coding things. So here I'm going to say y sub 0. I'm going to put in 1. I'm going to put in x sub 0. I'm going to put in 0. All right, so k, always I'm going to start at the 0 step. Then the next step is you hit equals, and it should bring up a function. You're just going to click on the one above it, and we're going to add 1 because it's just the step size go up by 1. Is this column absolutely necessary? No. This is a waste of life, right? But I like to have it. And then we're going to have dx, and then here, yeah, dx is fine. And then we're going to have that as 0.1. Okay. All right. So this is equal to whatever this is, and we go ahead and hit save. This is equal here. You can hard code this if you like. That's fine too. All right. So let's type in our function. Our function equals what? In this case, it is 2y minus 1. So it's 2 times, and you're going to hit 2 times, and then you're going to hit this cell minus 1 and hit enter. All right. Then we'll actually type in stuff now. So this is equal to, it's a cell above it plus this cell. But this cell, we want to preserve row and column. And so you just use $signs to do that. If you're typing this in Excel, you just type in $sign. You will have to have some basic Excel skills for this class or some basic C++ skills. One of the two is required. And we just go ahead and drag this down. There we go. And I want to find what the value is at 1, right? That's what I want to do. So I want to find the value, find y of 1. That's the goal. That is our goal. So let's go back to this. All right. So this y1 is equal to the step above it plus this times, and then our step size. But remember, our step size needs to be column saved. And so you just save it like this. I'll go ahead and drag this down. Now it says 1.1 because we haven't done this. And then here, this is fine. We just drag this down. Ta-da. All right. Okay, so what do we get here? So here, we get the answer to be 3.15 something, right? So let's write that down. Can we still go through it by hand? I'm not following what's going on. We can do, just because I want to finish class on time, the answer will be, you can just contact me later. We'll do it later. Okay. All right, so here, so if I continue this down to 10, right, I'm going to get, I got what, roughly 3.596, which is because at the 10 step size, I get what my y1 equals, right? Now, if I redid this for 0.05, well, here, the way I built my spreadsheet, it makes it really simple. All I need to do is just change, I want to change what this is. So I type in 0.05. Now I want to go for where x is 1, and I get 3.864 roughly. And so here I have y of 1 is equal to, or approximately equal to 3.864. Now, I know what the actual solution is. The actual solution, if we actually solve this out, y is equal to e to the 2x plus 1 all over 2. That's the actual solution. And y actually at 1 is 4.195. Oops. Uh-oh. So let me just kind of review this real quick. So here, often smaller is better, but not always. And so the smaller step size we choose, the more accurate our slope is at that point, and the more we do this. And so smaller step size for this class will almost always mean more accurate. In advanced mathematics, you can have things go funny if you get odd step sizes. So how do we do this again? So what we do is we just follow these two equations. And let me just wander through how we got it again. So here, this is our initial condition. 0 was our initial x, and 1 was the initial value. We plugged that into this function, and we got the initial slope at that function, which is 1. Then I'm going to move my step side forward in the x. So I'm walking this little delta x forward, right? And so I go to 0.1. And to do that, we just solve this equation right here. x1 equals x0 minus, or plus, the change of x. Then, so I just plug that in, I get 0.1. My y is equal to where we started, which was 1, plus my slope. My slope was 1 at that point. And how far did I walk? Well, I only walked 0.1. So my rise over run, so how much I gained as I walked my slope, it would be 0.1 in this case. So I get 1.1. And so I put that there. Then at the new point, I'm going to calculate my new slope. Well, my new slope, I'm at 1.1. Here I put it in this, and I get 1.2. So here I'm just plugging that in. 2 times 1.1 minus 1 is 1.2. Then I can do my next step. So 0.2, because I take my 0.1, add my step size, it will be 0.2. Here, I'm going to take my 1.1, where I was before, 1.1, where I was before, add to it my slope multiplied by my step size. So 2.1 times 0.1, which gives me 1.22. Okay. All right. But no one does this by hand. Well, you guys can. But here you're going to show the values, and here we can do this. And here, as long as I have it up, let's do 0.01. I think I'll have to add a couple more rows. Hi. We're almost there. Ta-da. And here I get 1.42. So that's a lot more accurate. So the smaller your step size, the much more accurate it becomes. Okay. So that's how you do numerical stuff and qualitative stuff. I'm going to look for something to give you to do slope fields that, when you do them by hand, just draw like 9 of them. I'm going to see if I can find some sort of free way to make it do it nice. Desmos has something, but it's not amazing. I want to see if I can find something amazing.